Okay, hello. This is my video for our homework assignment for chapter number 19. In this chapter, we're starting to look at mechanical vibration and problems that have to do with vibration and oscillatory motion. And so a lot of the problems have to do with pendulums or springs and things that oscillate. And so in this first problem here for this homework set, we're given this diagram here of this pendulum with the angle theta and the length L labeled, and we're told that this is a simple pendulum, and the first thing that we're asked to find is the amplitude of the motion in degrees. And so to solve this problem, the first thing I did was just write out some of the given information and what we know about simple pendulum motion. And so we were given our maximum velocity here of 0.4 meters per second, and we were also given the period for this pendulum is 1.3 seconds. And since it's a simple pendulum, we know that this is the equation for a simple pendulum, and we are asked to find this theta m value, our maximum theta value, which is the amplitude of the motion. And so in order to solve this, I recognized first that we had everything we needed to do to find our natural frequency omega n, because we were given our period, and we know that this is the equation for omega n. And so solving that, we could get this for our omega n value in radians per second. And then since this tells us it's a simple pendulum, we also know that the natural frequency has to equal the square root of g over L. And since we just solved for omega n, and we know g is 9.81, we can plug those in and solve for what the length of this pendulum is, and that comes to 0.41995. And then from there, now that we have that information, we can continue to try and solve the problem. And so from our lectures and the textbook, we also know that this relationship holds true, that our omega max, which is also theta dot, has to equal our theta max times our natural frequency omega n. And so going back to our kinematics relationships, we know that V has to equal R omega, and those are both max terms, and R in this instance is the length of this pendulum. And so replacing that, we can solve for omega max and get that omega max is V max over L. And we wanted to do that because we were given Vmax in the problem, and we just solved for L. And so now we have both of these terms here. And so plugging that in here and setting it equal to theta w omega n gives us this equation. And now looking at this, we have everything in this equation except for our one unknown, the amplitude theta m. And so plugging in the Vmax that was given in the problem, the length that we solved for, and our natural frequency term omega n, we can plug all of those in and just solve for our theta value. And plugging that in, it comes to 0.19707 radians. And the question asks us to find that in degrees, so converting that into degrees here, we get 11.29 degrees. So that is the answer for part A in this problem. Part B wanted us to find the maximum tangential acceleration of the bob. And so to solve for that, we go back again to one of the equations that was given to us in the lectures. At the same time as this, we were also given this equation for our acceleration, theta double dot max. And so looking at this, we just solved for this in part A, and we have this from part A as well. But we don't want our angular acceleration, we want the tangential acceleration. And so going back to our kinematic relationships, we know that A tangential equals alpha r, or in other words, in our instance here, that has to equal theta double dot times L, because L is the radius here. And so just dividing by L, we can set up this equation here, and then from there all we have to do is plug in our known information from part A and from what the question gave us. And we can solve that to find that our tangential maximum acceleration is 1.933 meters per second squared. And so that is the second answer for our first question. Okay, so for problem number 2 here, we're given two different diagrams. The first diagram here has a system of springs that are in series, and the second diagram has the same springs, but they're placed in parallel when they're attached to the weight, pulling them down. And so the problem also gives us the period of both of these systems. We're told that the diagram here where they're in series has a period of 5 seconds, and the diagram where they're placed in parallel has a period that's shorter, it's 2 seconds. And what the problem wants us to find is the ratio of these spring constants that will make this true, that will make those periods true. And so from our lectures in the textbook, we know that adding springs to find an equivalent spring is actually the opposite of what you do when you want to find an equivalent resistor. And so for springs in series, we add the inverses 1 over the spring constant. But since there's just 2, we can do K1 times K2 over the addition of the spring constants K1 plus K2. And then in parallel, it's just a matter of just adding the spring constants K1 plus K2 together. And so once we know those relationships for the equivalent K value for both of these diagrams, we can use what we were told in the problem about the periods to solve for that ratio. And so we know that the period is 2 pi over omega, and we know that omega for the springs equals the square root of K over M. And so all I've done here is mark omega for series with an omega S and omega parallel with an omega P. And then I've replaced K here with our equivalent K value for these two different situations here. So this is K equivalent for the series, which I've plugged in here, and K equivalent for the parallel, which I've plugged in here. And then from there we can create a relationship between the period and these K constants here. So these are the given periods in the problem. We were given the series period of 5 seconds and the parallel period of 2 seconds. And we can square that and set it equal to the ratio of our equivalent K values here. And so from there, it's just a matter of doing some algebra to be able to find out what that relationship of the spring constants K needs to be for us in this situation. And so reversing this fraction here, so we can multiply by the reciprocal, gives us K1 plus K2 squared over the denominator K1 times K2 right here. And then we can FOIL this out here to get a quadratic equation here. And then this term here was just multiplied to the other side. And so since we have this quadratic equation here, we can plug that into our quadratic formula, which gives us this relationship here. And then from there, we just need to do some more algebra to factor out so we can pull the K squared out of this term because it's squared in both of them. And then doing some algebra here, we can combine the K2's and divide them under to get a final answer here for our ratio of the spring constant. So the ratio of K1 over K2 in order to make the periods 5 seconds and 2 seconds, depending on if they are placed in parallel or series, turns out to just be 4. And so that is the answer for this one. Okay, so this is problem number 3. And in this problem, we're told that we have a building and that the second floor of this building deflects back and forth 40 millimeters. And this is because there's a piece of rotary machine rotary machinery, and as it rotates it's unbalanced, and so its rotation causes a deflection in the second floor of the building. We're given the mass of that rotary machine, and we're also given that the deflection is 40 millimeters. The first thing the problem wants us to find is an equivalent spring constant of the floor system, and so if there was a spring that was causing this oscillation, then what would the equivalent spring constant be that would cause that? And so to start with, I just drew a quick diagram here that shows the mass in that equivalent spring with the constant K that we're trying to find. And so to start off with, looking at the system here, we know it must be in equilibrium, and so W for that system has to equal the spring constant K that we're trying to find multiplied by our displacement term here, which can be either be S or this delta term here. And so in order to solve this, we can rearrange this so we have our weight here, and we can divide that by our displacement. And so our weight is given in the problem, that's the 3,500. Gravity we know is 9.81, and we're told our displacement is 40 millimeters. And so solving that, we can find the equivalent spring system for this deflection in the floor, and it would be 858.375 newtons per millimeter. And then we can take that value if we want and multiply it by 1,000 to get it into Newton meters, which is a more common unit. So we have this value here in Newton meters for our spring constant. The second part of this problem wants us to find the speed in RPM of the rotating machinery, so it can avoid the natural frequency. So basically, if something resonates at the natural frequency, it will amplify and it could cause damage to the building, so we obviously want to avoid that. So we need to make sure that we are not at this natural frequency. And so in order to find that, we need to find the natural frequency and then convert that into the speed of this motor to make sure that the rotating piece of machinery is not rotating at that RPM. And so we know that the natural frequency in hertz, the equation for that is right here, so we need to divide by 2 pi to convert omega n into Fn into hertz. And so we know omega n equals the square root of our spring constant K divided by our mass m, and so we can plug in from part A the spring constant we found, divide that by our mass that was given in the problem, the 3,500 kilograms, and then divide that by 2 pi after we take the square root, which gives us a natural frequency in hertz of 2.492 hertz. And then all we have to do is take that term and convert it into RPM. And so to convert hertz into RPM, we multiply by 60, which gives us 149.5, which is our final answer here. So the speed cannot be 149.5 RPM. If the speed of that rotating machinery rotates at this RPM here, then it would oscillate the floor at the natural frequency, and that deflection could amplify and cause damage to the structure. And so that is the answer for question number 3. Okay, so this is my work for this problem number 4. And in this problem here, we have this diagram here with this cylinder, and it's pinned to this horizontal surface here. And then there's a spring, an identical spring, attached to each side of this surface. And so the problem tells us that this system is displaced to the right 12 millimeters. And it wants us to find the period of vibration for this system. And then it also wants us to find the magnitude of the maximum velocity of this bar. And so in order to find that, the first thing we need to do is try to find the natural frequency omega n, and then we can use our relationships from there to be able to solve this problem. And so what I've done here is draw a free body diagram for this system broken up. So I drew a free body diagram of the cylinder and then this bar. And since the bar is being displaced to the right, we know that the force of these springs is going to try and restore this system back to where it was. And so both of those spring forces are going to be pushing to the left. And so if we use our equation, the sum of the forces equals mass times acceleration, we have mass times acceleration, and we can add up the forces in the x direction here. And then we can do the same thing for the cylinder here, but over here I designated the m as a big M to differentiate between those two. And both of those masses are given to us in the question. And so the next thing I did to solve this problem is write out some of the relationships that we know that relate theta to our velocity or our acceleration. And then from there we can use these equations from up above and try to eliminate some of our unknown variables. So we can plug those in to eliminate our f, theta, and p from up above. And so doing that, we come up with this equation here. And then using this equation, we can actually use what we know about the formula for the natural frequency to set up an equation for the natural frequency, because this is now in the form that we like it in. And so, yeah, so this is the form that we wanted to get the problem in order to be able to work with it. And so taking this and the equation we know for our natural frequency, we can write this equation here for omega n squared. And then, like I said, everything else was given to us in the problem, so we can just plug in the given masses and spring constant K of 5 kilonewtons per meter. And then we can take the square root of both sides to find out that our natural frequency omega n is 27.735. And so now that we have that information, we can actually answer what the question wanted us to find. And so to find the period, we know that the period is 2 pi over omega n. And so plugging in omega n, we have the period for this vibration of the system, which is the answer to part A. And then for the velocity max, we can take our natural frequency and multiply it by our displacement, which was the 12 millimeters, which gives us a Vmax of 333 millimeters per second. And so that's the answer for question number 4. So for problem number 5 here, we have this uniform disk, the problem tells us, that is placed in between this C channel here, and we're told that it's welded to this channel at B and at A, and that it's welded to these elastic rods here that are able to twist, similar to a spring tension. And so basically this uniform disk here is acting like a torsional spring that can rotate. And then we're told that this spring has a couple applied to it, or a moment, that causes it to rotate 8 degrees, and then afterwards it is released, and that gives it a period of 1.3 seconds once that couple is removed. And the first thing the problem wants us to find is the mass of this disk, given the radius and the period. And so drawing a diagram of what we're given here, I drew kind of a top view of this disk here. And we can see that it's been rotated to 8 degrees, and then afterwards it equals our kinetic diagram over there. And so in order to solve this, we first know that for a torsion spring, T has to equal K times theta. So we replace the X with a theta term for a torsion spring. And so rearranging that, we can solve for our spring constant K of this torsion spring system here. Because we were given the couple here, and so converting the 500 into Newton meters gives us 0.5 Newton meters, And then converting the 8 degrees into radians gives us this term here, multiplying by pi over 180. And so solving that, we can find that K for this torsion spring is 3.581 Newton meters. And so that is our K value. Then, looking at this problem here, we can take a moment about this center here, the origin, and doing so gives us this term here. And that is equal to our I alpha term, or in this instance alpha is our theta double dot. And then from there we can just rearrange this equation to get it into the standard equation that we're always looking to get it into this chapter. And so rearranging this, it equals this. And once we have our equation into this form, we know that this part here is our natural frequency omega n squared. And then from there we can plug that into our formula for the period, because we know that the period equals 2 pi over omega n, and we can replace omega n with the square root of k over I. And then we can flip this fraction here to bring that up into the numerator to remove the complex fraction. So from there, we're after the mass of this disk here in the torsion spring. And so if we can find out the inertia here, then we can set that equal to what we know the inertia is for a uniform disk, and then we can solve that for the mass in that term. And so that's what I've done here. We have the same equation here rearranged to solve for the inertia I, and then we were given the period. We solved for the K value up above, and so we can plug those in and find that our I value for this problem is 0.1533, and then we can set that equal to the I value that we know for a disk, which is 1/2 mr squared, and we were given the radius, and so we have everything in this equation except for the mass. And so we can solve for the mass of this uniform disk, and it comes to 21.3 kilograms. And so that's the answer for part A. Part B tells us that there was one of these rods removed, and it wants us to find the period of vibration if that happens. And so removing one of these rods will cut our K value, our spring constant, in half. And so calculating our new K value by dividing by 2 gives us a spring constant of 1.791. And then to find our period, all we have to do is plug that into the equation that we found here up above, because we know our I value that we calculated, and now we know our new K value. And so plugging that in here, solving for our new period, we find that our new period is 1.838 seconds. And so that is part B for problem number 5. Okay, so looking at problem number 6 here, we have this uniform cylinder, and we're told that it's pulled down this incline 0.4 inches, and then it's released. And so looking at this problem, we kind of have a before and an after. So position 1 was when it's pulled down the hill, and then position 2 is once it goes up the hill. And so looking at that, we recognize that we can use energy, our equations of energy, to be able to solve this problem and be able to find out what the problem wants us to find. And so the first thing the problem wants us to find is the period of vibration. And so I drew a diagram here to help me look through the problem. I labeled the forces on it, and then I labeled that we have our first position here, position 1, and then after it's released it goes to position 2, and that distance is 0.4 inches. And so to find the period, like I said, we wanted to use the energy equations, and so we know that potential energy before plus kinetic energy before has to equal potential energy after plus kinetic energy after. And so looking at this before, we have no kinetic energy because it has not been released yet, and our potential energy is coming from the spring here. And so we have 1/2 k times our distance that we can find from our drawing here as our first potential energy, and then after we have our kinetic energy because it is moving, and that comes out to this term. We have our rotational term plus our translational term, just like we saw in chapter 17. And then we have our potential energy for position 2 as well. And we can take all of those terms and combine them together to get this long equation here. And then trying to simplify this, we can just factor out some of these parentheses and simplify this as much as we can, which gives us this equation here. From there, we need to find another equation that we can use in this, and so I decided to take a moment about the bottom here where it touches the ground, which would remove the friction force and the normal force. And so taking a moment at that position there gives us this equation here. And then up above here, looking at the relationships here and this beta angle of 14 degrees given to us and the radius of 4 inches that was given to us, we can create an equation for the height here, which turns out to be r theta times sine of beta. And so plugging that equation into our moment equation right here, we can simplify this equation to get this after that h value that we found up here has been plugged in. Once we have that equation, we can use this equation 1 and 2 here to be able to simplify this and finally get it down to an equation that's a little bit more manageable. And so after doing all of that algebra, we end up with this equation right here. And then from there, we can make the substitutions to get our omega n term, our natural frequency term, into here from the equations that we have, and so that gives us this value here. And we know that our I value, since this is a uniform cylinder, our I value has to be 1/2 mr squared, and so we can replace that there. And so once we put that in, this will simplify even more, and we've gone from this really large equation here and all of that algebra and substituting everything in to get our omega n value of 2/3 times k over m. And so that's really useful to us now that we have this equation here for omega n squared. We can take the square root of those and find out what omega n is. And so using our relationship that we've used many times in the past for period, relating it to frequency here, we can divide by omega n, 2 pi divided by omega n, which is the square root of this term here. And we can solve that to find our period because we know that k was actually given to us in the problem as well as the mass. And so just plugging those in gives us our answer for part A, which comes out to 0.715 seconds. For part B here, to solve this part of the problem, we know that our max velocity, the question wants us to find the maximum velocity of the center of the cylinder for part B, and we know that that equation for Vmax has to equal r theta dot, and we know that theta dot has to equal theta m times our natural frequency omega n, and so we can do that quick substitution there to give us this equation. And then from there we know our radius is 4 inches, so to get that into feet we divide our radius by 12 and then we multiply by 2 pi divided by 0.715, which is our omega n term and our theta term, and then just plugging all of that into our calculator, we find our final answer for part B. Our max velocity is 0.293 feet per second for this system here. And so that is the answer for part B for problem number 6. Okay, so problem number 7 here is another problem that we want to use the equations for energy and work to be able to solve the problem. So in this problem here, we basically have two disks here that are the same, and they're attached together using this rod here, rod AB. And we're told that these disks roll without sliding, and so we don't have to worry about these disks sliding when we solve the problem. And we're told that these disks oscillate back and forth slightly, making small oscillations in the system. And we're asked to determine the frequency of those small oscillations. And so to start this problem off, I decided to just solve for some of the variables that we would need later on when we're using the work and energy equations. Because we're given the weight, 6 inches, and so we need to convert those to masses. And then we're also going to need the inertia terms, and since we are given them, we can find the mass, and we're given the radius here, we can just solve for those inertia terms I now, and then we can use those moments of inertia later on, instead of having to deal with that later. And so we know that since the disks are the same, mass A equals mass B, and so we just divide the 8 pounds that was given to us by gravity to get the mass there. And then we can do the same thing for the mass of the rod. We're told the mass of the rod is 20 pounds divided by gravity gives us the 6.21. And then for our inertia of these disks, we know that the inertia of a disk is 1/2 mr squared. We just found the mass for these disks, and we're given the radius in inches, so we can convert that to feet and plug both of those in to give us this for the inertia value. And so from there, we also want to use our kinematic equations here to find some relationships that we're going to need later on when we're doing the energy and work problem portion of this problem. And so we know that our velocity of the mass center has to equal r omega, and we know that omega is the same as theta dot, and our radius is 6 inches or 1/2 of a foot, and so our velocity will be 1/2 theta dot. Similarly, for the rod here, we can do a similar process, except the radius is 2 inches out of 12, and so that comes to this here, which is 1/6. So now that we have that part out of the way, we can actually start to solve this problem using the energy equations. And so basically the goal here is to use this equation where kinetic 1 plus potential 1 equals kinetic 2 plus potential 2, and so we need to find both of those. And so I drew a real quick diagram here of position 1 and position 2. So during this oscillation, I decided to make position 1 when this has rocked to its max position, where it's displaced, it's at its maximum. And position 2 is when there's no displacement, just like it's drawn here in the diagram. Both of these are flat and they're not rotated at all. And that will also be the point of maximum velocity, which we can use to our advantage. And so looking at position 1 here, when the disk is displaced, we have no kinetic energy because they've come to a rest at the max position. And we have all potential energy, and so our potential energy for this position will be cosine theta of however much it's displaced, that angle, times our weight of the bar AB. And so that is our potential energy for the first half of this equation. For position 2, right here, this is our kinetic energy term, and so there's a lot of different terms that we had to consider for this, and so we had the potential energy, or I mean the kinetic energy of translation and the kinetic energy of rotation for each cylinder. So this would be cylinder 1's kinetic energy, rotation, and translation. So here's translation and here's rotation. And then cylinder B, same thing, we have the translation term and the rotation term. And then our rod just has the translation term. And so we have those 5 terms there, which gives us this long equation here. But from there we can plug in all of this information that we took time to find at the beginning of the problem to help simplify all of this down. And so actually we have almost all of these unknowns. The only one we don't have is our theta dot, which is a good thing. And so that's what I've done here. I've plugged all of those things in. Since we know that these disks here are the same, we can combine these 2 terms with these 2 terms and just multiply it by 2, and so that's what I've done here. And then this is for the rod. So plugging all of that into our calculator, it simplifies really nicely to this right here. And then for our potential energy at position 2, there's no cosine angle because it's not displaced, but we still have negative omega AB, or WAB, times 4/12, which is the 4 inches converted into feet, which gives us negative 80 over 12. So after all of that, what we can do at this point is take these 4 terms that have the dots on them, the potential and kinetic energy terms for these 2 different positions, and we can set them equal to each other just like this equation here shows. And so doing that after we've simplified all these terms gives us this as position 1 and this as position 2. From there we can solve for theta, which gives us this right here for theta squared. Taking the square root of that gives us a theta m value of 5.7224. Now that we have that, we can look at this relationship here to try and find omega n. Since we now know our equations for omega, or theta dot and theta, we can plug those in and finally find out that omega n is 5.7224 radians per second. And so we're really close to the answer now, but the question wanted us to find the frequency of the small oscillations for the system, and so we want that frequency term to be in hertz instead of radians per second. And so taking this frequency term that's in radians per second and dividing it by 2 pi converts it to hertz, and so that gives us a value of 0.911 hertz. And so that is the answer for part 7. And so as the system here oscillates back and forth with small oscillations, those oscillations will occur at this value right here of 0.911 hertz. Okay, so for problem number 8 here, we're once again going to use the work and energy equations to be able to solve the problem. In this problem we have this pipe here. We're told it's a pipe that's suspended from these cables, and we're not given any numerical values here. We're just given the ratios here. So this is length L for these cables, and the distance from this axis to the end of the cable here is A over 2. And we're asked to determine the frequency of oscillation when the pipe is given a small rotation about the axis OO prime. And so the pipe here is oscillating back and forth along this axis. And so I started by drawing this diagram here to help me visualize that. So from the top view we can kind of see that this darker pipe here is before, and then it oscillates to this dotted line here, and it will continue to oscillate back and forth. And so looking at that, we can create a couple kinematic relationships that will help us later on. And so we know that A prime has to equal B prime because they are the same distance from the axis here, and that those have to equal this radius here, A over 2, times the amount of rotation theta, and that also has to equal L alpha. And so we can create those relationships to help us in the problem. So from this we can rearrange this and solve for alpha. And so just taking this and dividing by L, we know that alpha has to equal A over 2L times theta. And that gives us a relationship here for alpha that we'll be able to use later on. And so, like I said, for this problem we want to use our energy equation, and so this is our energy equation, that kinetic 1 plus potential 1 equals kinetic 2 plus potential 2. And the two positions I chose for this problem was before, when there was no rotation, and then the after position is when it's oscillated to its maximum rotation before it begins to oscillate back. And so looking for each one of these four terms so we can plug it into this equation, start here with the before position. So before, we know that there is no kinetic energy. It's not rotating at all, it's just at that position. But there is potential energy there. And so the potential energy equates to mgy, and in this case, looking at our diagram here, we know that y is L times 1 minus cosine of alpha will be our angle. And taking this 1 minus cosine alpha term out here, we can actually use a trig identity to turn that into a sine equation. And then using the small angle theorem that we learned about in the videos and in the textbooks, we can actually say that sine of theta is approximately equal to theta. And so using that approximation, we can eliminate the sine term out of that. And this alpha term here, we can actually replace with this A over 2L times theta. And so squaring that and replacing it with this alpha here gives us this equation right here. And so putting that all back together, we're replacing this 1 minus cosine alpha term with this term here. And these have to stay. And so one of the L's will cancel, and we're left with this as our before potential energy. And so our after position also has potential and kinetic energy terms. For the after position, there will be no potential energy, but we will have a kinetic energy term, and that's rotational. So we know that that has to equal 1/2 I of the center multiplied by theta dot squared. And in the problem, it tells us that this is a uniform pipe, and it's rotating about the center of the pipe. And so we can replace the I term from the value in the textbook, which is 1/12 ma squared, right there. And then, like I said, the potential energy in position 2 is 0. And so now that we have these four terms, we can plug them into this equation, which gives us this equation here. And then rearranging that so we have the equation that we always look for, we can actually find out what omega n is, our frequency, and then we can divide that by 2 pi in order to get this in terms of our frequency in terms of hertz. And so that gives us a final answer for this problem of the square root of 3 times gravity divided by this length L of the cable, and that whole thing divided by 2 pi. Okay, so this here is problem number 9. In this problem, once again, we're not given any numbers, but we're actually trying to find an equation. So for this problem here, we have this pendulum here, basically a ball attached to this rod or string, and we're told that it's a simple pendulum. And we're also told that this collar here that is attached to the pendulum is going to be slid to the right, which of course will cause this pendulum to swing outward like we can see in the diagram here. It will swing out a distance of x there. And we're told that the relation for which this is forced to move horizontally is this equation right here that is given to us. And we're asked to find the range of values for omega f, for which the amplitude of motion of the bob is less than delta m. So basically we want to find an equation where our omega f value must be greater than, so we have an equation that is less than what our omega f value can be for these conditions to remain true. And so to start with, I just rewrote the equation that was given to us and then drew a picture here of our pendulum after it had swung out this distance here that's marked. And I labeled some of the things that we know about it here. So we know that this length L here remains the same when it swings out, and it will swing out an unknown angle theta. And the distance from here to here was given to us as x, and I've called the distance that this collar swings x sub c, which will be less than this x value here. And so to see how much of a difference there is between this xc value and this x, we can actually use geometry to be able to determine what that relationship is. And so looking at this, that's what the equation is I've written here. So we have this distance x has to equal this distance x sub c plus whatever this distance is from here to here, which is L times sine theta of this angle. And so that's what I've written out right here. And then from there, all I did was rearrange this equation and solve it for sine of theta. So we know that sine of theta has to equal x minus x sub c all over this length L. After that, I decided to use our kinetics equations for force equals mass times acceleration. And so before doing that, I of course drew a free body diagram and set it equal to a kinetic diagram. And so for our free body diagram here, the forces acting on the ball of this simple pendulum is the tension, which is going up and to the left, and then the force of the weight, which is going straight down, which is mg. And that has to equal our mass times acceleration going to the right, and we know that our acceleration is also equal to x double dot, so I've replaced that. And so doing these two equations here, summing the forces in the x and y directions, gives us these two equations. Looking at the free body diagram and the kinetic diagram, we can tell that in the x direction we have the portion of this going to the left, which would be negative t sine of theta, and that has to equal this mass times acceleration in the kinetic diagram. For the forces, some of the forces in the y direction, there's no forces acting up or down on this ball in the kinetic diagram, and so that term would be 0. And so we have the tension going upwards, which would be t cosine of theta, subtracted from mg. And so all I did here was add that to the other side of the equation. So t cosine theta equals mg. And because this theta angle is considered a very small angle, we can say that cosine of theta is the same as 1. And so we can say that t is approximately mg because this angle is very small. From there, going back up to this equation here for the sum of the forces in the x, I realized that this equation for the relationship between x and x sub c that we created can be subbed in right here for negative t sine of theta. And so taking this term here and plugging it in for sine of theta gives us this equation right here. And I also added this term over to the other side to make it positive, which set it equal to 0. And so at this point we pretty much have our equation in the form that we like to see it in when we're solving these types of equations. And so that's what gives us this equation here. And looking at this, we know that this term right here is the omega n term squared. And so taking the square root of g over L tells us that omega n has to equal the square root of g over L. And so from that we can figure out the steady state equation for this system here. And so the steady state of this equation is actually comes out to be this equation right here, where we have the delta value over 1 minus the ratio of our omegas squared. And then from there we can square both sides of this equation, which gives us this. And then if we go back and look at what the question is actually asking us to find here, we need to find the range of omega f values for which the amplitude of the motion of the bob is less than the delta term. And so to find that, we need to set this less than the delta term squared. And the squaring it just makes sure we're not dealing with the negative numbers there. And so we make the assumption that if this x squared term is equal to this, then what will this ratio of omega sub f over omega n be? And so solving that, we can find out that it is equal to 0 and 2, and then we can take the square root of both sides of that, so it's equal to 0 and the square root of 2. And then putting that back into our greater than less than signs gives us this inequality here, which is what we're really looking for. So for our purposes here, we can ignore the left hand side of this equation because we're looking for terms when it's less than the delta term. And so all we do here is multiply our natural frequency omega n to the other side, and we come up with this equation for omega f has to be greater than the square root of 2 of omega n. And so that is what we're looking for there. And then from all of this work we did here, and looking at this equation that we created, we recognize that omega n is equal to the square root of g over L. And so we can substitute that in here to get our final answer. So the final answer for this problem is, in order to find the range of values for omega f, it must be greater than the value of square root of 2g divided by L. And so that's the answer for this problem, problem number 9. Alright, so this is the last homework problem number 10 for the chapter 19 homework assignment. And this was a pretty interesting problem, actually. It had some interesting concepts in it, and it used what it called a dash pot here type of spring, which was something that was kind of new. I had to learn a little bit more about what that is before I was able to solve the problem. But basically in this problem we actually ended up using conservation of momentum to solve it, which we hadn't done up to this point in this chapter, so we had to go back and use some of those concepts that we learned earlier in the semester. But basically in this problem here we have this block A that is dropped onto block B, and block B is suspended by this spring with a spring constant K, and this dash pot that I mentioned earlier that has a dampening coefficient C, and both values K and C are given to us in the problem, as well as the height that A is dropped from and the weight of both of those blocks. And in this problem, the question wants us to determine the maximum distance that the blocks will move after the impact. And we're also told that there's no rebound, so once A impacts B, they basically stick together. And so we need to know how far this system here compresses the spring and the dash pot. And so to start this problem, I drew this diagram here of the blocks A and B, and we can see the spring and the dash pot here that are connected to them. And so, like I said before, we're going to have to use conservation of momentum to solve this, and so this is the equation for conservation of momentum that we've been using this semester, that we've learned. And so here we have the mass of A and times the velocity of A before the impact, plus the mass of B times the velocity of B before the impact, and that has to equal the mass of A plus the mass of B times the velocity after. And we know that the velocity of A after and the velocity of B after will be the same because the problem tells us that there is no rebound. So they're going to stick together. And so plugging in what we know into these equations here, we realize that we don't have the velocity of A here, but we can figure it out using kinematics, and so that's what I've done here. We know that VA has to equal the square root of 2 times G times this height H. So converting the H from millimeters to meters and plugging those in gives us this equation, and then plugging that into our calculator, we can find that the velocity of A before impact is 3.962 meters per second. And of course the velocity of B is 0 because block B is at rest until the impact of A occurs. And so that's what we have on the left side of this conservation of moment equation. And then on the right side here we just have the two masses of 9 and 4 kilograms added together, multiplied by the final velocity. And so in this equation here, the only thing that we're missing is this final velocity of the system. And so we can solve for that final velocity and find out that the final velocity is equal to 1.29 meters per second. And it's important to recognize that the final velocity here can also be expressed as an x dot term, and that is traveling downwards in the downward direction. So the next thing we need to find out for this problem is what the static deflection will be for this system. And so this here that I've written out is the equation for the static deflection. And we have everything we need to solve for that given in our question here. So we can plug in the mass of A, the term for gravity, our spring constant K of 1500 newtons per meter, and that comes out to a negative 0.02619, and so that is the static deflection that will occur for block A. And so the next thing we can do is figure that we can set x equal to 0 and look at the equilibrium position for both of those blocks together by setting x equal to 0. And so by doing that, we can set up this equation here where c subscript c equals 2 times the square root of k times m. And once again, we have these unknowns given to us in the problem, so we can solve for this unknown here by just plugging in the given values into our equation and solving it. So that comes out to this value here. And looking in the textbook, we can look at the equation. It gives to us. It's under 19.44 in the textbook as I'm looking here, and it tells it that this relationship is true, and allows us to use this equation here for the oscillatory motion of this system. And so this equation here looks really familiar to us from previous math equations where we've had to deal with oscillating springs before as well. And so this is the main equation that we want to use for this, but some of these unknowns we can still solve for. And so the first thing we can do here is actually solve for an expression for omega sub d, and plug that in right here and here into this equation that we have. And so we know that omega sub d has to equal this equation here. And then C was given to us in the problem, the mass was given to us in the problem, and our dampening coefficient was given as well. So plugging all of that in, our value for omega sub d comes to 6.094 radians per second. And so we can go ahead and plug that into this equation. The other thing we can solve for in this equation is our constants C1 and C2, and we can find those using our initial conditions. And so these are the initial conditions that we were able to obtain. For example, this right here is the velocity term that we found up above using conservation of momentum. And so using these initial conditions and plugging them into this equation, we're able to solve for the constants C1 and C2. So we can first solve for C2 by plugging in x naught here. And so plugging that in, we know that the time is 0 when x naught is equal to this negative 0.02619. And so that gets rid of a term here and allows us to simplify this and solve for C2. So doing that, we get this value here for C2, and then now that we have C2, we can go back and repeat the process using our other initial condition to find out what C1 is. And so that's what I've done here. Solving for C1, just plugging all of those in, and the C2 that we just found gives us our value for C1 right here. So on the next page here, what I've done is I've taken this equation here, I've plugged in the omega sub d that we found and our two constants C1 and C2. And that gives us this equation here at the top of the page. So from here, after we've plugged in those conditions, we can recognize that our max deflection occurs when x dot is equal to 0. And so we can set this term equal to 0 so we can solve for the max deflection that the question wanted us to determine, and that will give us our total distance. So then it's just a matter of plugging in a 0 for this x and solving this equation here for our time t. So basically we're just plugging in the 0 and then simplifying this equation down by multiplying things through, and then we know that tangent is sine over cosine, and so we can divide those across and solve for our time t. And then by taking the arctangent of this right here, we can find out that the time at max deflection is 0.1253 seconds. And now that we have that time, we can use that time to find out the distance that this occurs over that time period by plugging it into this equation here. And so plugging all of that in, we find that our xm value, our maximum deflection value, is the 0.0307. So at this point we're almost done with the problem. The only thing we have to do is remember the quantity for static deflection that we calculated before and add that to our x max term here to give us the actual total that these blocks move together. And so adding those together gives us this value here, which can be converted into millimeters to match the units of the problem. And so after all of that work, we finally find our final answer. So the total distance that these two blocks move after block A impacts block B will be this 56.9 millimeters. So that is the final answer for this one and the end of this homework assignment. So thank you for listening. Bye.